Now, generics, the most important thing that was added to the language in Java 5, making the language a lot more flexible and a lot better to use than it was before. So thinking about the difference between Java and Python, the very different way that the source code of these languages looks like. Java, once again, so explicitly typed language that all the data that exists in your program, you have to give the explicit types of it, and from those the compiler can then infer the type of every possible expression and verify at the compile time that you are only ever using all data in a way that it's consistent with its type and not trying to use any of the bytes in any different way. So this Java type system, we can think of it, it's like a leash that we voluntarily putting around our necks so that we can walk like a dog in a well-disciplined manner. That we're telling that the Java compiler, this particular data is supposed to be that particular type, and that's how I intend to use it. So if the compiler ever catches us trying to do something else with those particular objects, then that's an error, and the compiler is supposed to catch me before the program even runs. So Python doesn't have this compile time typing. So both Python and Java are still strongly typed languages. Every object existing at the runtime has a type, knows what it is, and then that determines what the object is able to do. It is just that in Python, this testing that can an object do a certain method, so then that's gonna be done at the time of the call, then you'll get some kind of a crash if the object doesn't have the method, whereas in Java, the compiler enforces at the compile time that all the data is used according to its type, and therefore in Java you know that you're not gonna get a runtime type error. Your program doesn't crash for that reason. It can crash for a host of other reasons, but at least not because of that one. So now the generics, let's look at the idea, the relaxation to this rule that all the data must have an explicit type at the compile time. With the generics we can say that there is a type, but that type is to be decided later. So whoever uses this class, then it's the later when they create the object. So then they have to decide what they want that particular type to be. So for example, array list here. So the syntax for a generic class is that the generic types to be decided later are given in angle brackets, conventionally one character uppercase type, because no class ever has a one character name, at least there shouldn't have. There is also, you can Google your choice of which of the 26 letters can convey some additional semantic information. E here standing for the E is the element type that is stored inside the array list. And in the method signatures, this placeholder type, even though we don't know what it is, the user's gonna decide it later. The type, they might use a type that is not gonna be written until 10 years from now. So how can our code be ready for it? So they can instantiate this placeholder type to be anything they want. They can make an array list of strings, and then the beauty of this mechanism is that you can have any number of these different type instantiations. You can have an array list of strings, array list of integers, array list of bank accounts. All of these coexist in the type system, they play along, but notice they are all separate types. They're not assignment compatible and such, and of course they shouldn't be, because they are different types. So the array list of strings can do something that an array list of bank accounts cannot do, and vice versa. Array list of strings, you can add a string to it. Now because, so looking at the methods, so notice in the method signature, you can use the placeholder name as if it were an actual type. So then in the add method, so if you have an array list of strings, So then because E is string, so then in those objects the add method expects you to give a string, and this is enforced at the compile time. And then the get method, notice what you're getting, you're gonna be getting a string. And when you have an array list of bank accounts, the very same get method, now you're gonna get a bank account. So different instantiations, these methods then have a corresponding difference in the type. So let's read through the example. So the pair, so this again philosophy difference in Java and Python. So Python has the arbitrary tuples there, and Java doesn't have this kind of concept, and not even in the standard library. Now the rationale, if I've understood it correctly, you can Google for discussion, why doesn't Java have a pair class out of the box? So is that this concept of a pair is too low level. So if you wanna represent something as a pair, like a dimension, the concept in a string. So dimension is a pair of integers, width and a height. So then you need the class to represent the higher level concept, and then you internally implement it using two data fields or such. But so you should be doing the high level concept, not the low level thing. So notice that in a generic class, so it is, you can have I guess like everything does have a real limit, but so the limit doesn't matter. So the type of the first element and the type of the second element doesn't have to be the same. So then both can be independently of others. So looking at the data fields, so we're gonna implement the pair as the first component and second. So their types are whatever the user later decides. If they make a pair of string and bank account, so then first is the string and the second is a bank account. But now the static members, so this one the rule is now more strict because of the way erasure is implemented under the hood. So many other languages like a C++ has templates. Like they look and feel the same in practical use, and in practical use, so all this stuff you don't need to make a problem for yourself, like if you don't have one. So if you just use generic classes, none of the complexity from the later in today's lectures, you don't need to make it a problem for yourself. But we do have to understand the consequences of the underlying mechanism when designing our own generic classes. And because of the erasure, so we'll get there why it is so. But the one consequence is because at the runtime, all of these different type instantiations are actually one and the same raw class pair without any generics. So well, now that I got to it, so the erasure, so it means that the distinction between these different type instantiations, like an array list of string versus an array list of bank account, these exist only at the compile time. But once the compile time hurdles have been passed, so then all these invisible fences, this voluntary leash that we put around our necks vanishes. But once the compiler has established that the code at the runtime, there is no first moment where it could violate this invisible fences. So the code at the runtime is gonna continue to run as if these invisible fences were there for real. So then this is the reason we make compile time checks to avoid the runtime checks. In Python, more has to be checked at runtime, and the Python program can crash at the runtime because of a type error. In Java, because of this compile time checking in the type system, once the program passes the hurdle of a compile time checks without any errors or even warnings, so then it's guaranteed that it cannot crash because of a type error due to runtime. I'm sure there's a whole bunch of asterisks there to qualify the statement, but that's the general idea. So now these types T and U, so they're gonna be later something we don't know now. Those might be instantiated to something that doesn't even exist until decade from today. But notice how T and U, we use them as types in the method signatures as if they were actual types. Now, because nothing is known about these types other that they are some kind of a type and therefore by definition subtype of the universal superclass object. So by that virtue, we know that they have the equals method and toString method and all those methods that every Java object has by law, inheriting from the universal superclass. Now maintaining a static count here, notice that we have only one count for all the pairs. We cannot have a count that is separate for different instantiations of the pair. So the methods, the accessors, we make all the data private as it should be. So a public accessor, and then we make a public mutator. So notice T and U are used as if they were actual types. Override the toString method. So it is the representation of the first and the second. For the equals method, so now the runtime checking, remember runtime, the distinction between different type instantiations of pair doesn't exist. You cannot test that it's a pair of the same instantiations as this one. All you can test that it is some kind of a pair, so if it is with downcast to the correct type, and two pairs are equal if their first components are equal and their second components are equal. Well, equality, so we know that when inheritance and subclassing comes to play, so it becomes a horrendous can of worms, but this is the best we can do at the moment. And for the hash code, so make sure that if these pairs are added to the hash tables, that they get spread around efficiently. So this general idea, so how do you define a hash function? Something that returns an integer slot index that the hash table is gonna try to put your object into. The wider and spreadier you spread these hash codes over the entire int range, the better for you. So we can ask, so when an object consists of multiple components, so those components know their own hash codes. Now way to combine these hash codes, so we multiply by primes often, and this is another trick, so bitwise arithmetic. Remember an int is a 32 bits, so this one right shift 16 steps, so the lowest 16 fall out and the highest 16 become the lowest 16, and then the other way around, the lowest 16 becomes the highest 16 bits, and both fill with zeros, and then the exclusive OR, so combining these hash codes, so to make sure that so this kind of non-symmetric when you have multiple components, that if you just XOR the raw hash values, so then swapping the component values doesn't change the hash code. So we gotta do something that is asymmetric, that makes a distinction between symmetric component pairs. And here, to finish this one off, so how do I know if I wrote a decent hash function? So let's sample. So let's create a set of that we're gonna be filling with some random pairs. So here I'm gonna be filling with a million randomly chosen pairs of integers. Notice again the auto boxing, so these are ints, but the pair of integer, so ints are automatically converted to integers. So create a new pair and add its hash code, add it to the hash codes that we've seen. So theoretically, so we could get, if we're really lucky, but so even with the most perfect hash function, there's always gonna be a collision for the combinatorial reasons explained in the algorithm course. So if we run this now, let's see how many. So 125 collisions out of million. So that sounds like it's about as good as it's gonna get.